Hello and welcome back to Precalculus. We are going to talk about the unit circle today, and we are going to set all of those trigonometric functions into the unit circle and also show where those triangles actually come from, the special ones that we have seen. So we're going to start with the unit circle, and the unit circle is called the unit circle because it has the radius of 1. So when we draw, and it's hard to draw on this ice pack, when we draw these axes, which are actually your x and y axes, then the radius over here is 1. So unit circle has radius equal to 1. Now, we talked a lot about those divisions and everything else. So now I'm going to put an angle, let's say right here, and say that that angle is pi over 6 radians, which is 30 degrees. Now, what you can see is that it intersected the circle circumference, and you can drop the line straight down. Now, we know this is 1 because that's the radius. Now, the bottom is no longer 1. It's something shorter. So we will call that value x value, and we'll call this a y value, which is actually projected here, right? That's the same y value. And we also know that there is a right angle here. So what you have is, again, one of those right triangles that we just learned about in our last lecture. So what I have in this case, right? What I have in this case is now the measurement of x and the measurement of y, and this point here are going to be those x and a y that we calculate. Now, what it turns out, right? If you maybe we can now let's zoom in and have this triangle larger over here. So what I have is angle theta. I know that this is 1, and I know that this is y, and I know this is x. And I know this is my right triangle. Right angle, I mean. So I have my adjacent, my opposite, and my hypotenuse. And if I write my 6 trigonometric functions now, those expressions, they're going to have x's and y's in them. And those x's and y's are actually the coordinates of the point on the circumference of the circle. So sine theta, looking at that triangle, is opposite over hypotenuse. That's just y. Wow. So sine theta is going to give me the y coordinate of the point. The cosine theta is adjacent over hypotenuse, that's x over 1, that's x. So cosine theta is going to give me x. So that means that my point xy is actually cosine theta, comma, sine theta if I know what the values are of those for the given angle. Now we also have tangent theta, which is y over x, cotangent theta, which is x over y because it's a flip, secant theta, which is the flip of cosine, that's 1 over x, and finally cosecant theta, which is 1 over y, which is flip of sine. So we were able to define all 6 trigonometric functions now using the unit circle coordinate x and y, which is just a point on the circumference which we get by the point right there, which we get by either computation or we can compute the trig with it as well, as you can see. So now, when we have the unit circle, we can think about connecting the triangle that we see in the unit circle with what we have seen before in our previous lesson. So, good. All right, so I have a circle, and let's say this is where the middle is, x and the y, 0, 0. And what I'm going to do is I'm going to draw the 45-degree. So this is our pi over 4 angle, which is 45 degrees. Now, actually, I don't have room for the 45 degrees there because I have to drop this one down now. And what you see here, we know this is 1. It's a unit circle, so radius is stretching from the center to the circumference. And we have our x and we have our y. So now, there are certain things that if you know geometry, right, you can figure things out here. Let's remember that we said that x is equal to cosine theta and y is equal to sine theta, and then that this point here is x comma y. All right, so now what do we know? If I draw a square and I draw the 45-degree line, which is the diagonal of a square. Well, since it's a square, we know that these lengths are the same, and this is the diagonal of the square. So now, if I use Pythagorean Theorem, I have a square plus a square is equal to diagonal square, because diagonal is that hypotenuse technically in that triangle below. And I hope you see that that's the same thing that we actually have. So 2a squared is equal to d squared. And then when you solve for d, you get a root 2. Right, when you square root both sides, you get a plus minus, but we disregard the minus because lengths are not negative. Right? Lengths are never negative because it's right. You have to have some positive length for a diagonal. You can't have -7. So we drop the negative from the square root, and we have d equals this. Now, when I look at my picture, I know that d is equal to 1. So 1 is equal to a root 2, which means that a, which is a side, is equal to 1 over root 2, which when I rationalize is root 2 over 2. Well, hey, a is equal to x is equal to y is equal to root 2 over 2. So we just figured out this way now that your cosine of 45 degrees or cosine of pi over 4 is root 2 over 2. And that was your x-coordinate, by the way, for the point. And then sine 45 degrees, which is sine of pi over 4, is also root 2 over 2, which was your y. Now, we had this in the other lecture from the special triangle that we had. And that special triangle had different measurements, right? It had 1, 1, and root 2 this way, right? But now we have it opposite. We have that these are 1 over root 2 each, and this is a 1. But that's okay. So now, if I draw another circle over here, just quickly, this point here, which is at 45 degrees, has root 2 over 2, comma, root 2 over 2 as the coordinates. Now, root 2 over 2, you can figure out, yes, root 2 is irrational number, right? And root 2 does not have a finite decimal, but it's about 1.4142, blah, blah, blah. But, even if you call it 1.4, then it's going to have like almost 0.7 on the measurement. So if we know that this is 1 all the way out to the x, because it's a unit circle, so radius has to be 1, when you drop this one is at 0.7, about 0.7, not exactly 0.7. And then your y coordinates also about 0.7 for that point. That's root 2 over 2 and root 2 over 2 for both x and a y. So now we can also find the location using the angle and the trig functions. We can find the location, x and y location, position on the circumference of the circle. Now, surely there's going to be more than one application where you will need to know your positions and speeds and all that stuff for some kind of circular motion. So that's going to be also in this mix. So now that I know cosine and sine and I know x and a y, well, guess what? I know x and a y. I can get all 6 of these, right? Because the tangent, right, of 45 is going to be 1, which is tangent of pi over 4, and that's going to be root 2 over 2 divided by itself, which is why it's 1. And that was y divided by x. Then the cotangent is x divided by y. It's also 1, right? And the other ones are root 2 and the root 2. So we have a lot of these interesting calculations. I want to take a look also at some homework exercises before we move on. But we already defined all of the 30, 60, and 45 previous lecture. This is more to see that you can get them from the unit circle as well. Now, some might ask, is it better to use triangles or unit circle? Unit circle is better because you see all of the divisions in the unit circle. We will also learn about reference angles. So triangles are not really useful They are very easy to understand to begin with because opposite, adjacent, and all of that kind of stuff. But everything that we are going to deal with moving on in the course, it's actually the unit circle where you need to have extensive knowledge so that you can deal with, as I mentioned, reference angle and some other things coming up. So we want to know unit circle very, very well. Now, we see that all of those triangles that we talked about before, they exist in the unit circle. But unit circle is going to give us so much more, right? And we will have to deal with those other things as well. So let's observe one more really cool thing that we can get from the unit circle. So let's say this is our unit circle here. And you take an angle that it's, let's say, negative pi over 4. So last class, not the last lecture, but before the spring break, like 2 classes ago in 4.1, we said that the positive angles are measured this way and the negative angles are measured that way. Great. So that would make this angle here negative pi over 4. Okay, sounds good. Let's actually do it this way. Negative pi over 4. You can also write it as negative 45 degrees. Now, do you see what it has as the coordinates? We know that the root 2 over 2 are the coordinates. You see, x coordinate stays positive, but the y coordinate becomes a negative because it's below x-axis. So I didn't have to recompute everything. I just look at the symmetry in the circle and decide which coordinate is positive and which is negative. So we have both positive over here, x and a y. Then we have x to be negative. Actually, let's do this. Plus x plus y, minus x plus y, minus x minus y, and positive x and negative y. Those are the 4 quadrants. So no matter where I am with my angle, and also, sorry, forgot to mention this, if I measure it this way, in which case it's measured as 7 pi over 4, they have the same point. They have the same point. Are they the same angle? No, but they are in the same location. The terminal, initial and terminal sides are in the same spot. We just went the different way around the circle. So one says negative pi over 4 and the other one says 7 pi over 4. But they land at the same point with the same coordinates. And immediately looking at these coordinates, what do I know? I know that my sine of negative pi over 4, right, is negative root 2 over 2 because it's a y value. And the cosine of negative pi over 4 is positive root 2 over 2 because the x coordinate is positive. Remember, we derived earlier, right here, that, well, actually, right here better, sine is y and cosine is x. So we just read that off of the circle. I don't have to do any calculations, right? I just look at it and I know immediately. So, wow, right? Cool. Tangent of negative pi over 4? Well, you are supposed to divide these two numbers, right? Because it's y over x. So it's going to be negative 1 for tangent as you go along. So in this unit circle, right, we can find a lot of different angles. We can get to them in a different way. But once you reach the point, that point has the set coordinates. Doesn't matter whether you went all the way from the left or from the right, from below or above, whatever you want to say in the circle. Doesn't matter which way you went around it, which is why we have the counterclockwise and the clockwise direction. And those, I hope, are self-explanatory. When you say clockwise, you know that which way the clock handles spin on a clock. Now I know it's becoming harder and harder to use those words because you guys are born with digital clocks, right? And you just look at the numbers. But yeah, it's a new era. So clockwise direction has negative angles, and counterclockwise, right, which goes up and left, that's the one that has positive angles. So counterclockwise is the default state for the trig, which begs you to wonder which one is backwards, math or clocks, right? Should we have designed clocks to go the other way? And the answer is yes, because this stuff is older than clocks. So believe it or not, this stuff is older than the clocks with the minute and the hour hands. So go figure which one is going backwards. All right. So that's some fun stuff. Now, one more thing. How about we flip these real quick? So my cosecant of negative pi over 4. Let's write the other three as well. Is going to be negative root 2. And then secant of negative pi over 4 is going to be root 2. And the cotangent of negative pi over 4 is just going to stay negative 1, obviously, because when you flip negative 1, you still get negative 1. Can anyone spot anything interesting regarding these minus signs? I'm just asking you to state the obvious, literally.
They're in the parentheses?
Well, that's all of the pi over 4s are negatives. I'm asking about the answers.
The signs stay the same?
For all of them?
Yes.
No.
No.
So which ones stay the same and which ones do not stay the same? Do we all see that? Again, I'm asking to state the obvious. Think about it. We have, no, think about it. Look at it. Negative, 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 negative. Those are the ones that have negative signs. The other two don't have negative signs. And we also know that secant and cosine are flips of each other, right? Cosine was adjacent over hypotenuse, and the secant was hypotenuse over adjacent. So they are linked, and they are the only two whose negative sign kind of disappeared. Well, it didn't disappear. We know exactly, right, where it went, because it was the cosine is the x-coordinate. The x-coordinate over there is positive, so obviously we're not going to have a negative sign because x-coordinate is just a positive number. But the fun and interesting thing here is that those are the only two that did that. All others have the negative sign. And that is connected to even and odd functions. Welcome back to chapter 1. I did say that chapter 1 will never leave. So all of those concepts from chapter 1, like graphing and shifting and transformations and inverse functions and composition, all of that will be back now to be done. And here it is, the even and odd functions. We also have domain and range. All of that stuff will be back. Now, what we see is, if you remember, the even was that f of negative x gave you back just f of x. And the odd, f of negative x gave you back negative f of x. Now that's exactly what we see here. Negative input, negative output. That's an odd function. Negative input, positive output, right? That's the even function. So for even functions, we have the cosine and the secant. For the odd functions, we have the sine, we have the tangent, we have the cosecant, and we have the cotangent. And those are the four odd trig functions. So what we actually have is that cosine of negative x is the same as cosine of x. Secant of the negative x is the same as secant of x. And then we have the other four. Sine of negative x is equal to negative sine of x. It kicks the x outside. That's exactly how the odd functions behave. And then the cosecant of negative x is negative cosecant x. The tangent of negative x is negative tangent x. And finally, cotangent of negative x is negative cotangent of x. So those are the even and odd functions. And the first time when you will come back to this to prove it, you will use it all the time. You will use this for the rest of this course. You will use it in Calc 1, and you will use it in Calc 2. The first time you go back to prove this in a different way than what you have seen up there with the unit circle is going to be all the way at the end in the last chapter of Calc 2. Like that's the next time you're going to see another approach to this proof, and why these are sorted as even and odd functions. So we used this one example over here, and we developed all of these, but it doesn't have to be exactly this. Could have been any value along, as long as it's symmetric for the same angle on the other side of the circle. And these functions behave in this way. So we will find later on the use for this, especially when we're solving, let's say, equations in graphing, and so it will pop up. It will pop up again. And now, as we are going near to, well, actually, no, we have actually a whole bunch of other stuff here that we need to talk to. You know what I never talked about? The flip functions. I never wrote down the relationship. So we understand that sine and cosecant hopefully, are flips of each other because the sine is opposite over hypotenuse and the cosecant is hypotenuse over opposite. So that's clearly opposite. Now it's opposite through the reciprocal property as like 1 over a value. So we can write that the cosecant theta is actually 1 over sine theta. We can write that the secant theta is 1 over cosine theta because they are opposites, they are flips of one another. And we can also write that the tangent theta is 1 over cotangent theta, which would make the cotangent theta equal to 1 over tangent theta. And finally, the sine theta is 1 over cosecant theta. I mean, that's the same formula, just flip it around. You just need 3, right? You just need 3 formulas, like these 3 formulas, let's say, because you can solve for the others by flipping these formulas. You don't have to go with all of them. But we'll write all of them here, so you have them all on one pile. So these are called reciprocal identities. And they are, again, the formulas, like the formal formulas, for us to link these functions, like the pairs, right? So we pair cosecant with sine, secant with cosine, and tangent and cotangent. Oops, I forgot the theta over here. Tangent and cotangent. Now, you can prove these very easily by just using your definitions from our last class, which is I already mentioned. Let's focus on, let's say, this one here, where we say secant theta is equal to 1 over cosine theta. So cosine is adjacent over hypotenuse, and the secant is hypotenuse over adjacent. So they're flips of each other. So if you want to put equal in between them, you have to put 1 over. And this is the same formula. It's just you look on the other way. You can swap cosine and secant, right? And you get the top formula. They show the same calculation from a different perspective. So we have that, and then we also have, because again, those in the right triangle line up the sides, we also have that the tangent theta is sine theta divided by cosine theta, and the cotangent theta is the cosine theta divided by sine theta. Now, this is something that, again, you can easily prove using those opposite and adjacent and all that stuff. Let's do one of them. Cotangent, for instance. So cotangent theta is equal to, and for the cotangent, we know that it was adjacent over opposite, right? So that's what we had when we defined it. Now, what do you have on the other side? You have a cosine theta divided by sine theta. So cosine theta is adjacent over hypotenuse, and the sine theta is opposite over hypotenuse. So now when you cancel the hypotenuse, you're left with adjacent over opposite. And there you go, same. So you can put them together. Now let's see if we can figure out some example from the book where they might give us something to find other values. Sine and cosine are given. Identify, use identities to find tangent, cosecant, secant. Okay, the other four. So these are the problems that would utilize these kind of things. Let's say problem 26 says sine of t is equal to 3 over 5, and the cosine of t is equal to 4 over 5. Get other 4. Okay, that's not going to be a problem at all, because I know the formulas. I know that the flip of sine is a cosecant t, and then just that's 5 over 3. Because the cosecant is 1 over sine, and that's just going to flip. The secant, which is the flip of cosine, is going to be 5 over 4. Perfect. And I just talked about these two equations, that the tangent, you can divide sine by cosine. Oh, great. Tangent t is going to be sine t divided by cosine t, and that is 3 over 5 divided by 4 over 5, which is 3 over 4. And for cotangent, you can either do the flip or you can do the calculation where cosine is divided by sine. Now, obviously, cotangent t would be better to just flip, right? Because it's faster than to do more calculations with fractions. And there they are. Other 4 trig expressions written down. We were given sine and cosine, and we were able to get the other 4. So that is really, really cool. So that was problem 26. Let's see what else they have. Okay, let me just see if I missed any of the key point. Yes, I did. Actually, I did a lot. I missed a lot. We need to talk about Pythagorean identities now. Yes, yes, yes. Pythagorean identities. Now, what you know when you say Pythagorean theorem for the triangle, you know x squared plus y squared equals to whatever, c squared, whatever. Right? And you have that in your right triangle like this, and the c is the longest side, and you have your x and you have your y, and everyone is happy, right? Well, hold on. Don't I have my unit circle? There's no way I can draw on this rocking ice pack. So we'll do this. So if I pick some angle, drop down this line, knowing this is x, knowing this is y, knowing there's my angle theta, and knowing this is 1, does the Pythagorean theorem apply for it? Hell yes. And did we say that x is equal to cosine theta and y is equal to sine theta? Yep, we said that as well. So x squared plus y squared equals 1 squared when you look at the picture, because it has to follow 2 legs, each one squared, right? So the sum of the squares of the legs is equal to the square of the hypotenuse. So now plug in sines and cosines and things. So x is a cosine, okay, plus y is the sine, okay, equals 1. And this is one of the most important formulas of any trig course. Sine squared theta, or x or whatever, plus cosine squared theta is equal to 1. There's your Pythagorean identity. We are going to use this a lot. I mean, everything from these two sections, 4.3 and 4.2 and 4.3, we're going to use a lot in every class. And I know this is a lot of information to dump in two sections, but trig is very rich and has a lot of good applications, very important. And yeah, we have all of these things on a pile. Now, once you have this one established and you know it, you can come up with two more. See, let me just write it one more time. If I divide through by cosine squared everywhere, if I divide through by cosine squared, what do I get? Well, sine divided by cosine is tangent. Okay. And then cosine divided by cosine is 1. And 1 over cosine is secant. Ooh. So I get a Pythagorean theorem, which connects tangent to secants. And if you divide by sine, you immediately see what happens. 1 plus cotangent squared theta is equal to cosecant squared theta. So these are the Pythagorean identities for trig, and we technically get them by replacing x with cosine theta and y with sine theta. It's pretty cool. Now, are there any problems where we can use these? Let's see. Hopefully there are. I actually don't see any, because we are going to have the entire section where you will have to use these a lot, but that's in chapter 5, I believe 5.1. So I don't think, yeah, I don't think that we have Pythagorean identities. Oh, actually, here they are. Ha, lied. Found them. Problem 36. I mean, they're very simple because you see the formula and you're done. Sine squared of pi over 3 plus cosine squared of pi over 3 is equal to what? Well, by the formula that it's boxed up there, we know it's equal to 1. But can we compute this and show that it's equal to 1? So let's say yes. So sine of pi over 3, everything squared, plus cosine of pi over 3, everything squared, is equal to what? Well, we already know from our last lecture that sine of pi over 3 is equal to root 3 over 2. And that needs to be squared. And then cosine of pi over 3 is 1/2. Now, these values, right, these values were in our previous lecture, the 4.3, right, that we did before this 4.2. I know it's confusing, but such is life. So I did not make up these root 3 over 2.5. We had them last time. And now when I square these values, I get 3 over 4 plus 1 over 4, which is 4 over 4, which is 1. I mean, whether you use the formula that was boxed to say that this is 1, or you do the computation, right? It has to be 1 either way. Doesn't matter which way you do it. So that was problem 36. Let's take a look at one more, problem 38, because it looks weird. Cosecant squared of pi over 6 minus cotangent squared of pi over 6 is equal to what? Well, it doesn't take a long time to realize that, because you move cotangent to this side by subtracting it, and you get 1. So we know answer is 1. But we want to compute it, right? And we'll start with the same trick, writing this square on the outside so that we can just focus on computing the trig identity. I mean, the trig function. All right. Now, we are going to use, because we don't really memorize the cosecants and cotangents and all of those things. We know our sines and cosines generally because they show up on the unit circle, and everything can be traced back to them. So sine and cosine are like the most important one, followed by tangent. And then the other three are all kind of mushed in the same category. We'll talk about you if we really have to. And the reason why, right, we discriminate against these and say we'll talk about you if we really have to, is because they can be turned into sines and cosines, right? So your cosecant is 1 over sine pi over 6, and your cotangent is cosine pi over 6 divided by sine of pi over 6. And that all stuff is squared. So as you can see, I am able to bring everything back to sines and cosines. So on the first one, I have 1 divided by 1/2. That's the main division line. And then minus, on the other one, cosine of pi over 6 is a half on top. And the sine, no, lies. Root 3 over 2. And the bottom is 1/2. And that needs to be squared. Now I'm first going to simplify inside the parentheses. So I get 2 minus, and over here I get root 3 squared. So 2 squared is 4 minus 3, and there's your 1 again. Now please observe which way I computed a cosecant. No one well, no, not no one. I mean, you're always going to find people that like to memorize everything and then forget it 3 days later. But in this case, right, note the way it was solved. We used the previous definitions we had, and we apply those, and by previous definitions of sine and cosine, right? And we change the cosecant into sine, and then we use the values. Now, some people might go, well, how do you exactly remember these? Well, first of all, it's practice. It's years of doing this. And also, I was interested. So obviously, that like takes care, the attitude takes care of the most of everything. If you have the right attitude, the rest follows quickly. So what do I want to do now? I want to show you this really awesome way of figuring these out. And these are generally the ones that you want to know. And they are done for 0 degrees, 30 degrees, 45 degrees, 60 degrees, and at the end 90 degrees, which are your pi over 2, pi over 3, pi over 4, pi over 6, and 0 radians. All right. Now, if you care to learn the trick, pay attention, don't write, because you can catch up later. But the trick, if you learn the trick, then it becomes very, very simple. What I'm going to do is I'm going to count 0, 1, 2, 3, and 4. And I'm going to divide everywhere by 4. And I'm going to take a square root in each. When you compute these, it will give you the value of sine for each one of those angles up there. So 0 divided by 4 is 0, square root of 0 is 0, so that's a big fat 0, meaning sine of 0 is 0. Square root of 1 is 1, square root of 4 is 2, meaning sine of 30 degrees is 1/2, or pi over 6. Square root of 2 we can't take, but square root of 4 is 2, meaning, we already know all of these values, but I'm just going to write them down here for at least sine, and then you can do the rest. Okay, square root of 3 I can't take, square root of 4 is 2, so I have sine of 60 degrees is square root of 3 over 2. And finally, 4 divided by 4 is 1, square root of 1 is 1, so sine of 90 degrees, which is pi over 2, is 1. That's how you read the chart. You just find the value. It's a sine of 45. You look at the chart, oh, root 2 over 2. That's why we have the chart. So it is so simple. 0, 1, 2, 3, 4, divide by 4, take a square root. When you compute those values, they give you the values for sine. Now, remember the cofunction identity? 90 minus theta? The cosine values were the same, they were just opposite, which is why you take the same numbers and you just write them backwards for cosines. And finally, you use your division, which was the identity we had right here. Your tangent is sine divided by cosine. Awesome. So going back to my chart, 0 divided by 1 is 0. These guys will cancel the 2, and when you rationalize, you get root 3 over 3. Root 2 over 2 divided by itself is 1. This one will be root 3, and this one is unidentified because, as you will see, you have a vertical asymptote there. Once we start graphing, right, you can't divide by 0, so 1 divided by 0 is undefined, and there will be a vertical asymptote at that location. So this is probably the best way to study these values, like draw this chart. We can do it the good old Eastern European way, right, for education. Just draw this chart 20 times. And if you don't know it by the time you did 20 times, just do it 50 times. And if you didn't figure it out by the time you did the chart 50 times, do it 100 times, which were my homework assignments every time I mess up any of these values. So, yeah. And yeah, if you and if you if you don't do the homework when the chart is assigned to do it 50 times, you just get kicked out of classroom, so you can go outside and play ball with your friends or something. And yep, no school for you. But you also don't have a second chance. And yeah, no engineering. So there you go. Well, I think now we should be good because we learned all the values and things. And we have the identities, the quotient rules, the reciprocal rules, the trig functions defined, even an odd is done. We'll need to talk about domain and range. I'm going to leave that for a function. Yeah, I think we're good. Ooh, one more thing. Luckily, we still have 4 minutes. Okay. It has to do, this is called periodicity, repetitive behavior. These functions are so good because of that. This is the feature that they have. They repeat themselves after some time. And that is evident on the unit circle, which is why it is in a section for the unit circle. So this is going to be the last thing, definitely. We will have to come back to this because we'll need this for equations later on. So I'm just going to draw this angle here, and I will label it, if I go this way, I will label it as 1, 2, 3, 4, 5 pi over 4, right? That's a 5 pi over 4 angle, because you have your 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, and then 5 pi over 4. Now, if you go the other way, this is what we already know. You have negative 1 pi over 4, negative 2 pi over 4, negative 3 pi over 4. So to get the same separation between the x-axis ray and the terminal ray that I have there, we can go the black route, which is 5 pi over 4, or the blue route, which is negative 3 pi over 4, to get to the same location. But hold on. Can I make a full circle and then land there? Yeah. Right? Right. Now, how much is that one? How much is the red one? The one that makes a full revolution from x-axis and then lands in the same location. So let me draw this red one nicely again. So you go the full circle and then you land there. So the black one is 5 pi over 4. The blue one is negative 3 pi over 4. The red one is the full circle plus 5 pi over 4. And that is 13 pi over 4, right? When you do the common denominator, multiply by 4 on the 2 pi side. So, wow, 13 pi over 4, and then plus 2 pi, I can go again, another 8, 21 pi over 4, 29 pi over 4. I can keep going, right? I can keep going. And I can keep adding 2 pi, which is why we can say that all angles of the form 5 pi over 4 plus 2n pi are going to land in the same spot. All of them. And that means that we have a lot of angles that will end in the same spot. Now, don't do this because obviously you're going to get a ticket, but right, real life example, when you have the circle and you have the let's say 4 streets feeding in, and you go into the circle, roundabout or whatever you want to call it. All right, let's put some grass over here. So you drive in and then you go around the circle and you get out. Right? That is actually your 3 pi over 2 angle that you took around. Obviously, you should not be going the wrong way. If you go the wrong way, then you just have pi over 2 angle, negative pi over 2. But you're probably going to be deleted if you go in a circle. Like every time is a miracle when you make it through the circle without being hit when everyone goes the right way. Imagine going the wrong way. That would be terrible. Now, why I say don't do this, it's a ticket. You go in, then you go about 5 times around, and then you go out. Yeah, that's actually a ticket. If you just go and drive in a circle, you're still going to end up on the same street. Yes, you wasted extra time because you went around the circle. You risked your life for extra couple of minutes, right? But you still end up in the same street. You came in on the same street. You came out in the same street. Just you went 5 times around it. So that is exactly what we are talking about over here. Your angle, the separation between the two black rays that I have, is the same. Now, which way am I measuring? Blue route, black route, or the red route? They all have the same angle at the end, but they have different values assigned to them, right? And that has to do with what we call periodicity. And we will see a lot more about the period of these functions as we move along because, right, this is this plus 2n pi, right? That will be something that we can say, yes, you get there, but if you make a full circle, you can still be at the same point, and so on. Now, it does look like that every point on a circle now can be represented infinitely many ways, and that's true, which is why we're going to learn something really cool very soon, reference angles. And we will never have to worry about this until we hit equations. So that's it for now, guys. Now we definitely got everything in. And I did skip over domain and range. I'll talk about it when we write down trigonometric function, sine x, right? And then we'll figure out what the domain and range and all of these things are. The next class, 4.4 and 4.5, but 4.4 is the one where we learned that reference angle I mentioned, and we put the end to this insanity that every angle can be represented infinitely many ways. So until then,